4.5 is dealing with implicit differentiation. This is another kind of differentiation process that we're going to be using when we have implicitly written equations. So first we're going to look over what is the difference between an implicit and explicit equation, and then we're going to figure out how to derive them. So explicit versus implicit. Just kind of a quick English lesson. Implicit is the implied statement. What are you implying when you say that? When we're looking at it in terms of math, what we're saying is y is somewhat hidden within an equation. You're going to have to kind of figure out where y is and where it stands. Explicit is stated clearly. This would be an equation like y equals x squared plus 3. Obviously, y equals blah. Okay, so we clearly know what y is equal to. Whereas in an equation that we're going to look for that are implicitly written, you're not so clear as to what exactly y is equal to. So just a quick statement, an analogy. If I were to implicitly accuse someone of something, let's say that there was a robbery at Sparky's gas station last night, and I walk into calculus class and I say, so there was that robbery at the gas station last night at around 7, and I look at Morgan and I'm kind of like, hey Morgan, I saw that you had like a lot of money in the backseat of your car. And didn't you tell me, Morgan, that you were going to Sparky's last night? And yeah, I think you did. All right, and then I walk out. That would be an implicit way of me accusing Morgan of being the robber. Versus if I just walk in the room and say explicitly, Morgan, I know you robbed the bank, and then walk out. Okay, so implicit versus explicit. Implicit is something that's implied. You kind of have to find the meaning. Explicit is blatant. Say it right out. So let's look at some examples of these. This is, do we know exactly what y equals? No, you would actually have to solve for your y in order to figure out what is exactly y equal to. So this is an example of an implicit. This right here, y equals blah. Okay, that's an explicit statement. This is so far what we're used to deriving when it's just y equals something. Same thing here, you could solve for your y, so divide by x. So if I were to write it y equals 1 over x, this right here is explicit versus this right here was the implicit. And finally, same thing here, this is implicit. Okay, y is kind of hid amongst everything. So knowing that now, what I'm going to have you do is consider these, because we're going to have to derive this and there's a certain situation that's going to come up. If I were to ask you to derive x squared with respect to x, well, sure enough, you would just say, alright, the derivative of this function with respect to x, that's the notation that we've been using, of x squared. So the derivative of x squared with respect to x, well, surely let's just derive around it. So you would use the power rule around that x and then drop that exponent by 1. Great. Alright, but now what if I asked you to derive y squared with respect to x? So here you have your derivative with respect for x as your notation, and then you have this y squared. And what you're seeing is I'm supposed to be deriving around x here, but my variable is y, so something's not adding up. So I'm going to say, consider this. Say I told you that y was equal to 2x plus 1. If you were to simply say, I want to find g prime, so g prime of x is equal to the derivative of this y to the 4th, and I wanted to derive around this, well, by just simply stating what we did for deriving in terms of x and deriving around that y, this would not be enough, and I'll show you why. So let's say that we do know that y is equal to this. Right? What we would have to do is we would have g prime of x is equal to the derivative, and then I'm going to plug in this 2x plus 1 to the 4th. So now what I hope you can see here is I need the chain rule. So the chain rule is needed. I'm going to have to say, alright, let's derive around this inner function. So I'm going to say 4 and then times 2x plus 1 to the 3rd. Alright, but then I have to go back and figure out what the derivative of this inner function is, so it's just going to be times 2. What I have done here is this right here is the derivative of my function y with respect to the inner function. But what you had to do is you had to make sure that you derive the inner function, or that dy with respect to x. So go ahead and derive around that y. But what you have to remember to do then is go back and multiply this by dy dx. Okay? One thing to keep in mind is if we ever just derive y, so y to the first, what you would say is, alright, here's 1, y to the 0, but then you would actually have to say times dy dx in order to derive this. So this right here is just 1, right? So it's just 1. So that's why if you ever derive y with respect to x, you're going to get this dy dx notation exactly. So this is a process for our implicit differentiation. We're going to combine the two things that we just went over, what is implicit equations, and we're going to combine this idea that we technically need the chain rule when we're deriving where our variable that we're deriving with respect to doesn't match up with what we're actually trying to drive around. So here are the steps. I would take a moment to write this down, but otherwise I'm just going to be using these step by step each time. Your first example is going to be number 1, and they give you this, and it says find dy dx by implicit differentiation. I'm just going to say diff. Okay, so what we're going to do is understand that this is our y, it is amongst the equation, this is implicit, so what we're going to have to do is use these 4 steps. So I'm first going to differentiate both sides of the equation with respect to x. So I'm going to have to differentiate this side, and I'm going to have to differentiate this side with respect to x. So now I'm going to have to use the sum and difference rule, so just piece by piece I'm going to derive this. And I'm also going to derive, or I'm not going to derive anything yet, but I'm just kind of setting myself up. So now I'm going to start using some of these rules. To derive x squared, I'm going to use the power rule. It's just deriving around x. We have 2x to the first plus. Now again, here is where we're going to say, well, I can derive around my outer function. I don't know what the heck y is. Y could be anything. It could have been the 2x plus 2, but I'm going to derive around it, so I'm going to pull down that 2, use the power rule, but then what you have to recognize is I'm trying to derive with respect to x, and because I don't know what y is equal to in terms of x, I have to multiply by the derivative of that inner function, so dy dx. Okay, so there is this term right there. I derived using the chain rule. I derived around the outer function, left that y alone, but used the power rule, and then I went back and said, but then you have to acknowledge that I would have to multiply by the derivative of that inner function, whatever it is. So equals, and again it was because this and this variable did not match up. And this is just the constant rule, it's equal to 0. The next step that you're going to be using is collect all terms with dy dx on one side and all of the other ones on the other. So I'm going to take this off, I'm going to subtract 2x from both sides, minus 2x. What we're going to get is 2y times dy dx equals negative 2x. And then finally what I'm going to say is I'm going to undo and solve for my dy dx. So this is its own term. We're going to solve for it, get it by itself, because that's what we're trying to find. What does that equal to? So I'm going to divide both sides by 2y, divide by 2y, dy dx is equal to negative 1x over y. And I don't even need that 1. It's just negative x over y. I do want to show you something. If you were to solve for y, I'm going to show you what you would get. You would get y squared equals 36 minus x squared, and then you would get y equals plus minus the square root of 36 minus x squared. You could derive that, and what you're going to get is the very same result as what you got here. However, what you do have to do for this one is solve it 2 separate ways. One is negative and one is positive. So I'm going to rewrite this. I'm going to rewrite this as y equals, and then 36 minus x squared to the 1/2. I'm also going to write it as y equals negative 36 minus x squared to the 1/2. If I were to derive this, so I'm going to derive that first equation, dy dx is equal to, and then I'm going to pull down that 1/2, derive around my inner function, to the negative 1/2, and then times the derivative of this inner function. It's going to be negative 2x. Okay, so then when I simplify this all out, This does go back to the bottom, so it's going to be 1 over 2 and then 36 minus x squared to the 1/2, and then all over on the top it's going to be negative 2x. So those cancel each other out. What I am going to get is negative x over 2 times, and then in parentheses, or I guess the square root of 36 minus x squared. Oh, sorry, this canceled out. That shouldn't be there. That 2 should not be there. Okay, so what I want you to see then is we have this negative x over y. What was y equal to? Well, when we solved for y, it was this guy right here. So there is that y. Interesting, huh? Likewise, if you did it with this negative, it would get us that plus negative. Okay, so either way it works. All right, number 7. We're going to do number 7. Oops. So this is the problem that I gave you. So again, I'm going to just follow those steps exactly. I'm going to derive both sides with respect to x at first, and then derive this side with respect to x. So what's going to happen is I do need the product rule within this. So when I derive this first term, because at first I'm going to use the sum and difference rule, so I'm going to need to derive what is x to the third times y to the third, minus what's the derivative with respect to x of this y equals, and then the derivative with respect to x of x. So this right here, so far all I've done was I've used the sum and difference rule, but now to derive this first term as part of that sum and difference rule, I need to use the product rule. So it's the first function, or that first factor, times the derivative of that second factor, plus, and then now I'm going to leave that second factor alone, but then derive the first factor. That right there is the product rule. Right? Then minus d dx of y, so equals d dx. So I have not done any differentiation. All I've done is I've shown what I need to do. I've shown the places where I'm going to have to derive. So here I'm going to get x cubed times, now let's derive this. We're going to need 3y to the second. That would be me using the chain rule, but again, these don't match up, so I am going to have to say, well, this I can't assume what y is equal to, so I do need to say that I just need to derive that inner function. Plus y cubed, that's going to stay exactly the same, times, now this one is the good old just normal power rule, because I am deriving x with respect to x, so we're just going to work right around that x. Okay, so that's that term, and then minus, now here's again that where that notation is important. You would have 1y to the 0, that's just 1, but then you would still need dy dx equals, and this right here is just going to be 1. Alright, so yes, I have derived everything. These dy dx's, those are just the result of me deriving. So here is one term, here's another term, and here's another term. What I am going to do is get only the terms with the dy dx on one side, so I'm going to eliminate this one by subtracting off y third times 3x to the second. And then so that's the same thing as minus 3y cubed x to the second. So I'm going to get x squared, or cubed, sorry, times, I'm going to put that 3 out in front, y squared times dy dx. That's that first term that's left on this side, plus negative, here we have dy dx. So I have just gotten all my dy dx's on one side. That was this right here. Collect all terms with dy dx on one side. And then on this side I have 1 minus 3y cubed x squared. So finally what I'm going to do is, because all of these terms have a dy dx, I'm going to pull that dy dx out, because I just want to get dy dx by itself. So what I have left, if I pull that dy dx from that term, it's 3x cubed y squared, and then what I have left here is just a 1, okay, a factor of 1. So there we have that, equals 1 minus 3y cubed x squared, and now what's going to happen is I can divide by this term, 3x cubed y squared minus 1 divided by 3x cubed y squared minus 1. This right here is what dy dx is equal to. So what I have just done is I have derived y implicitly. So even though I didn't know exactly what y was, I did this process in order to figure out, well, what would the derivative of y with respect to x be if I were to do it. So I do want you to recognize one difference. I mean, sometimes you can take an implicitly written equation and write it explicitly, which I did here, and then you can derive. Sometimes like this, you can't even write it explicitly, so that's why this implicit differentiation process is necessary. I would say this: if I asked you now, find the derivative of this function at the point 1, 2, if I asked you that, instead of just now putting in x, you're going to be able to put in y as well. So just in all of these x and y values, you could plug in a 1, and then 2. Okay, so that they didn't ask you to do that in this problem, but they will be in some of the others. So there are your practice problems.